Hi everyone. In this video, I want to tell you about symmetric operators on the space of periodic functions and use the identity we discussed in the last video to show that the second derivative is going to be a symmetric operator in this space, which will lead us to talking about Fourier series in the future. So first I'll recall the concept of a periodic function. So a periodic function of period p is a real number. Let me write it like this. It's just any real number, and it's positive. Is a function f from the real numbers to the real numbers, satisfying a certain property that f at a point x that's equal to f at the point where you translate x by p, so x plus p for all x. Yeah, so this is kind of an algebraic way of saying what it means for a function to be periodic of period p. But basically, if you draw the graph of a function like this, so you draw here the y-axis and the x-axis, and you draw the graph of a periodic function of period p. So here's p, and here's 2p, and negative p. Basically, what happens to functions like this is that if you know what they do between 0 and p, you would know what they do in all other, I mean, this is not going to be perfect because I'm drawing by hand, but right, they repeat at every interval of size p. Okay, and so basically you can understand such a function by only looking at one of its cycles, right? So if you look at what it does on any interval of length p, then you will know what this function does on all of R, all of the real line. And you don't need to choose the interval starting at 0 from 0 to p. You could choose like p over 2 to like 3p over 2 somewhere here, right? And it repeats anyway. It doesn't matter where you center it. So because we're going to be talking about cosines and sines, those have period 2 pi, as you know. What I'm going to do is I'll actually call, from now on, I'll denote the period by 2L. By 2L. Okay, so L now is a real number which is positive as well. And the cycle that I'm going to focus on for our periodic function of period 2L is just the centered interval, right, from negative L to L. If I know my function from negative L to L, then I will know it, let's see, like this. Then I'll know what it does as it continues because it just repeats, right? So it's going to do something like that from here, something like this. Right? So it's just kind of a nice way to kind of have our interval symmetric to the, with respect to the y-axis, basically. Right? So here's the y-axis and the x-axis. Okay, and so one interesting thing about periodic functions is that well, they form a vector space. So I should say the set P2L of, and I'm gonna ask some regularity of my function, so I'll say infinitely differentiable meaning they have these functions, all the functions in the set. This is a set of functions, so just a collection of functions. They all have derivatives of all possible orders that you want, right? So they have first derivatives, second derivatives, third derivatives, as many derivatives as you want. So they're infinitely differentiable. That's what I mean by that. Periodic functions of period 2L. So the set of periodic functions of period 2L is a vector space by that, I don't want to get into the axioms or anything, but what I mean is if you have two periodic functions of period 2L, g of x, two functions in P2L, then their sum, f of x plus g of x, is also in P2L, meaning if f of x is infinitely differentiable in periodic of period 2L, and g of x is infinitely differentiable in periodic of period 2L, then f of x plus g of x is also infinitely differentiable, and it also is periodic with period 2L, is also in P2L. So that's one thing that makes this a vector space. It makes it an abelian group, I guess. But the second thing is if f of x is some function in P2L, and so periodic function of period 2L, and c is a real number, then the function c times f of x is also periodic of period 2L, right? So basically, in this set, you can add functions together, and you can multiply functions by a real number, right? So once you have addition and scalar multiplication, you say that the set is a vector space. I mean, nice properties that they have to satisfy. Don't want to get into that, right? So basically, you can kind of think of this set of periodic functions, P2L, as Rn. It's very similar in certain ways, at least, to Rn. The thing that is a little bit more complicated about it is that it actually has infinite dimensions. It's an infinite dimensional vector space. But you just don't want to think about that because that's just an extra complication that's not going to make you feel good initially. But, you know, it's just like Rn. And it's so much like Rn that it also has a dot product. Right? It has a nice, so instead of calling it a dot product, we usually call it an inner product. We reserve dot product to the famous one in Rn. So P to L, rewrite that. So P to L has an inner product so you can think of it as a dot product. which is defined by if you have two functions, f of x and g of x, and you want to do basically the dot product between them. That's defined to be, so they both are periodic of period 2L. You can focus on this fundamental cycle between negative L and L. That kind of describes them completely. So this dot product is actually the integral from negative L to L of f of x times g of x dx. You just integrate one times the other. Okay? So you should read this just as in Rn. It should, in your head, you should think of this as v dot w, right? So a vector in this vector space is a function, right? So f of x is just like the v, and g of x is just like the w. And instead of having, so maybe I should say that this whole equation, you can think of it as a formula for what the dot product is. In Rn, the dot product is you multiply the components, right? You take v1 w1, v2 w2 plus vn wn. That's how we define the dot product in Rn. In this space of periodic functions, that's how we define the dot product. Okay, but if you have a space with a dot product, then you can talk about a symmetric operator, because that's all we needed. Get one more page here. That's all we needed to define a symmetric operator. And so why don't we do that? So a linear operator so I'm gonna call it T. So from B to L to B to L is defined just like before, is a function such that it respects the addition and the scalar multiplication. So let's just say 1 t of f of x plus g of x is equal to t of f of x plus t of g of x, and t of a number times a function, or a number times a vector, is you just take the number out, or you can take the number out of a linear map. Yeah, so a linear operator is defined completely in the same way, and we know that a linear operator is symmetric if it satisfies that identity that we talked about in the last video. So a linear operator is symmetric if, well, the dot product, we wrote it in terms of the dot product, right? So t of f of x dot g of x, you can just slide the t to the other side. It's f of x dot t of g of x. Right, so that's what it means to be symmetric. Oh, that's weird. So that's that's what it means to be symmetric, right? This should remind you of the equation that we had in the last video. We said an operator is symmetric if t v dot w is equal to v dot t of w. right? It's exactly the same thing, but now our vectors are these periodic functions. Okay, so maybe let me write a little diagram here. What we did is we took, in our case before, in finite dimensions, our vector space was Rn, but now we have a different vector space, which is the set of periodic functions of period 2L, P2L, right? And a vector in here right? So a vector in Rn is just a set, an ordered set of n numbers, right? So v1, v2, n tuple vn. While here, a vector in here is a periodic function f of x with period 2L. And infinitely differentiable. I'm gonna not say that all the time just because it's a little long, right? And here we have a dot product. If you have two vectors, you can dot them together. You have a dot product in Rn. Wn, and you have a dot product in this space of periodic functions, which we denote like this. Which is integral from negative L to L of f of x gx dx, right? So these two things should be kind of parallel in your mind, right? Back and forth between Rn and the set of periodic functions. So let's now talk about the second derivative operator. Okay, so let's maybe write a proposition, which is basically a theorem that is not that important, or a theorem that's not that complex, but proposition is that the operator, the linear operator, which is the second derivative. I'm going to denote the second derivative like this with a partial symbol, even though there's only one variable. I just think it looks a little bit better than the ddx way of writing it. Is symmetric. Okay, so it's a symmetric operator. Again, I'll remind you, one of the very nice things about symmetric operators is that first, is the spectral theorem that they satisfy. So the spectral theorem says that every symmetric operator first only has real eigenvalues, and second, it has the vector space will have a basis of eigenvectors of this operator. Okay? So we'll see that this is still going to be the case here, and this basis is going to be exactly what's going to give us the Fourier series expansion of functions. So let me write here proof. I want to show that this is true. I'm going to show to you why that's true. So to show that this operator is symmetric, we must show that given any two functions, any two functions in PL and P2L. Then you can slide this operator to the other side of the dot product. That was a typo. Yeah, so, and there's no real trick here to do this. Well, there is, I guess, a trick in a way, but we just start on the left hand side and we try to get to the right hand side. That's all. Okay, so we start with the left hand side of that equation and we just write what it means and we see what we can do there. Right, so this dot product, let me write exactly what it means. This is the integral from negative L to L. Second derivative of f, let me write that as f prime prime. That's how we usually write it. Times g of x dx. So it's just this integral, right? And what we want to do is send this derivative to the g. Yeah, from f to g. And we have a nice trick to do this, which is integration by parts. Right? Integration by parts sends the derivative to the other function. So I'm going to do it slowly here for you. I'm sorry, I hope I don't bore you, but I'm going to call u of x g of x, and then u prime is going to be g prime. And then v prime of x, I'm going to call f prime prime of x. V of x then is the antiderivative, just f prime. Okay, so that's a little integration by parts scratch work. So this will turn into, you have the boundary terms, which is going to be u of x times v of x. So it's g of x times f prime. That's going to be evaluated at the endpoints, so at x equals L and x equals minus L. Then you get minus the integral from negative L to L of u prime v, which is f prime g prime, or g prime f prime. All right, f prime g prime dx. Okay. Now, one of the very nice things that happen here is because we are considering periodic functions. Well, this function here, g of x times f prime of x, is also periodic, as you can see, right? So g of x plus 2l times f prime of x plus 2l is going to be equal to g of x times f prime of x, right? So this is still in a periodic function. So if you compute these boundary terms, you plug in L in this, and then you subtract plugging in negative L, you're going to get 0. Yeah. So I'm not going to write it out explicitly, but this is equal to 0 since periodic, since it is periodic. Okay, and so we are only left with that integral minus the integral from negative L to L f prime g prime, and we want a second derivative on g, so we integrate by parts again. Yeah, want to send the f prime, that prime on f to g, so I'll write another scratch work here, u of x. This is the one that we're going to take a derivative of, so it will be g prime. U prime will be then G prime prime. V prime is going to be F prime. And then V of x is the antiderivative, F of x. So still just a little bit of scratch work here. Let me add to my previous. And so if you integrate by parts, here we get the boundary term. That's going to be u times v, so g prime times f of x. Evaluate that at x equals L, x equals minus L. And then here you get, with a negative sign, there's a negative sign right here. And so minus this boundary term, and then minus the integral with this negative sign turns into plus, plus the integral from negative L to L. And now u prime times v, which is f of x times g prime prime of x. Oh, prime was ugly. Dx. And again, because these functions are periodic, this function here, g prime of x f of x, is also periodic of period 2L, and this boundary term is again 0, since they are periodic. And so this is just equal to this integral, which we can write as a dot product. This is the dot product, or the inner product, of f of x with the second derivative of g. So we're done. We showed here that the second derivative of f of x, inner product g of x, is equal to f of x, inner product second derivative of g. And this works for any function f of x and g of x, provided that they are infinitely differentiable. We're taking derivatives of these functions, and they're periodic of period 2L, right? So it works for any two f of x and g of x, right? So this means, here's our QED. We show that the derivative, the second derivative, is a symmetric operator on the space of periodic functions. And on the next video, I'll talk about the eigenvectors and eigenvalues of this operator and how they relate to the Fourier series of expansion of a periodic function. Okay, see you then.